Namaste. Welcome to the next video of Machine Learning Practice course. In this video, we'll implement linear regression with SGDregressor. SGDregressor uses gradient descent or iterative optimization techniques for learning the parameters of the linear regression model. SGD offers a lot of control over optimization procedure through a number of hyperparameters. On the flip side, we need to set these hyperparameters to right values in order to make SGDregressor work for training the regression model. In this collab, we will study how to set these parameters to right values. We begin by importing the packages that are required for this demonstration. So notably, we are importing SGDregressor from sklearn.linear_model module. Then we have validation_curve from model selection, and rest of the other packages are from the previous collab. Hence, we are not explaining them in detail here. As a usual practice, we set a random seed at the start of the notebook. Here again we are using a shuffle split as a cross-validation strategy with 10 folds, and we will set aside 20% examples as test examples in each of the folds. We will load the data, which is the California housing dataset, and split it into training and test. Further, what we do is we divide the training data into two parts, train and dev. So this particular dev part is what will be used for tuning the hyperparameters. So with this arrangement, we hold back the test data set for evaluating the performance on the SGDregressor. Okay, so now after loading the data and splitting it into three parts, train, dev and test, we'll build the baseline SGDregressor model. So to begin with, we instantiate the SGDregressor with default parameters. We only set the random state to 42. All other parameters are left to their default values. Then we train the SGDregressor model with the features and labels from the training set. After fitting the model, we obtain the scores on training and development sets. So here we calculate the mean absolute error on the training set as well as on the development set. In order to calculate this error, we use the actual labels and the predicted labels from the trained classifier. We repeat the same procedure on the development dataset, and then we print this mean absolute error for both the datasets. And you can observe that the mean absolute error is too high. The baseline model doesn't seem to train or doesn't seem to work that well. This may happen due to large training rate. Let us investigate this issue by training the model step by step and recording training loss in each step. We studied that SGD is sensitive to feature scaling. So what we'll do is we'll first add a feature scaling step and then check if we get better mean absolute error. So we add this feature scaling through pipeline. So now we have a pipeline that has got two stages. In the first stage, we perform the feature scaling with standard scaler and followed by SGDregressor. Then now we call the fit on the pipeline object with the training features and labels. Once the model is trained, we calculate mean absolute error on training and development set. So now you can see that the error has reduced drastically. So error is now 0.51 and 0.63 on training and development sets respectively. However, the error is still high, and now what we'll do is we'll run the SGDregressor step by step and investigate issues with training. So we have discussed how to run SGDregressor step by step in our slides. So we instantiate SGDregressor with warm start equal to true and tolerance equal to minus infinity. So again we are going to use a pipeline construct, and the error rate is this particular learning rate, which is eta 0, is set to 0.01, which is a default value. And we are actually instantiating this particular thing for the visualization purpose. We are not using this value inside SGDregressor right now. So hence SGDregressor uses eta 0, which is the default value, which also happens to be 0.01. Then what we do is we perform the training in a loop. So in every step we call the fit on the pipeline object with training feature matrix and labels. And since warm start is equal to true, what happens is it uses the parameter values that were learned in the last iteration, and then it updates those parameter values in the fit function. So since now after this step we have fresh parameter values, we calculate the fresh loss obtained on this pipeline. So we calculate mean squared error here with the actual labels and the predicted labels. So after we are done with 100 epochs, or after running this particular process for 100 iterations, we get loss values for each of the iteration. We plot this loss value in what is called as learning curve, and this learning curve is what we have used again and again in machine learning techniques course, where we have iterations on x-axis and we have mean squared error on y-axis. You can see that the mean squared error reduces initially and then it goes up and settles somewhere over there. This could happen due to large training rate. We'll first reduce the training rate by a factor of 10 and retry the training. So now we are using eta 0 as 0.0001, and we are setting this eta 0 value in the SGDregressor constructor. So now everything from the previous step is exactly the same, except that we are setting the value of eta 0, which is the initial learning rate. And just to remind you that the learning that will be used here, learning style, will be inverse scaling, and with inverse scaling the learning rate is reduced in every step. So here we are setting the initial learning rate. We again repeat the same process where we train SGDregressor step by step, and we collect the mean squared error in every step and then plot it on the learning curve. Now we have learning curve which is looking something like this. So what we can see here is as we do more and more iteration, the training loss goes down gradually. And this is kind of a good sign, and this is an ideal learning curve where training loss reduces monotonically as the training progresses. Sure, this loss is not reaching to the zero value, which is ideal value for the loss, which is mean squared error. And this could be due to underfitting, but that's a different issue. Here we seem to have found a learning rate that helps us to reduce the mean squared error monotonically as the iterations increases. So we can also find out how many iterations SGD took before reaching the convergence criteria and how many weight updates were performed. So here SGD pipeline has taken one iteration and it has performed 11,611 weight updates. You can see that the mean absolute error on the training set is 0.53, whereas on development set it is 0.51. So there is an alternate way to fix the learning rate, that is to validation curves. Let us study how to do that. Here we have to provide the list of values of hyperparameter to be tried. Here the hyperparameter is the initial learning rate, which is eta 0, and we are specifying the values that we want to try for eta 0 in the ascending order. Then we instantiate an object of validation curve with the estimator, the training feature matrix, training label matrix, and we are setting the parameter for which we want to calculate this validation curve. And since we are using a pipeline construct, the parameter name is the name of the step double underscore the name of the parameter. So we can see that in our pipeline object, SGD step was denoted by identifier SGD capitalized, and hence we refer to this parameter as capital SGD double underscore eta 0. So this is the parameter on which we want to calculate the validation curve. We want to vary this parameter, and for each parameter value we want to calculate the training loss and test loss. And we can also specify what kind of scoring mechanism we want to use. So here we have specified negative mean squared error as a scoring mechanism. We also specify the cross validation that we want to use, and we are going to use shuffle split cross validation. We also specify the parameter range to be tried, and this parameter range is what we had specified initially. So this list also goes as an input to validation curve. So validation curve returns training score and test scores. So we convert these scores into error by multiplying them by -1. And we plot these errors on this particular plot, whose x-axis is the value of the whose x-axis has different parameter values that we tried, and eta 0 was the parameter of our interest, and we tried four different values of that. So this is the first value, second value, third value, and fourth value, and for each of those parameter values we got training error and test error, which are plotted over here. And on y-axis you have mean absolute error. You can see that the training and test error reduced initially as we increase eta 0, but beyond the point it just shot up. So this is the point where the test error is the least, and hence we select this particular value of eta 0 as the value that we want to use as the initial learning rate. We can also plot the standard deviation in the error, and this is slightly complicated because you can see that at the end the standard deviation is too high, and that results into some kind of unstable estimation for the test error. So hence we select this eta 0 point where the standard deviation is also not that high, and we have lowest training and test error without much of the variation. So this is how you can use validation curve to set any hyperparameter to decide the right value for the hyperparameter of your interest. So again, it's a very simple process. We have to provide the list of values to be tried, and then we simply instantiate the validation curve object and gather the training and test errors and plot them in the on the validation plot, and then fix the value of the hyperparameter where the test error is the lowest. So we can use this process in order to set any other hyperparameters. Not only in case of SGDregressor, but any other hyperparameters that we may encounter while training different machine learning algorithms. Now that we have fixed the value of initial learning rate, let us train SGDregressor. So now we are going to train SGDregressor with maximum iteration to be 500, early stopping equal to true. So here we are going to stop SGDregressor with early stopping criteria. And in order to set early stopping criteria, we also need to provide the validation fraction. So we are setting aside 20% examples as validation examples, then n underscore iter underscore no underscore change, which is number of iteration for which we do not see much change. We do not see change greater than the value of tolerance, that is set to 5. And we also have to set the tolerance, which is again 0.0001. So this is the machinery for early stopping, or these parameters are kind of set for early stopping. Then we also set average equal to 10 in order to use averaged SGD. So this will essentially start averaging SGD after it sees 10 samples. Now with this setup, we train the regression model and calculate the mean absolute error on training and development sets. So we got mean absolute error of 0.57 and 0.56 on the training and development sets respectively. SGD took 7 iterations and it performed 81,271 weight updates. So the number of weight updates is equal to iterations into the number of examples in the training set, and that will come out, if you do that maths, it will come out to the number of weight updates. So by default, SGD uses inverse scaling as learning rate. Now what we'll do is we'll change the learning rate, and here we have changed the learning rate to constant. And when we use constant learning rate, the learning rate specified in eta 0 is used across all the iterations. So you can see that when we use constant learning rate, it took us about 8 iterations and 92,881 weight updates. We get slightly better performance on this, and that you can observe by finding the reduced absolute error in comparison to the earlier model. Here the error was 0.57 and 0.56 on training and development sets respectively, that is reduced to 0.53 and 0.51. There is one more learning rate, which is adaptive learning rate. In adaptive learning, what happens is it uses the initial learning rate as long as we reach the convergence criteria. When the convergence criteria is reached, the learning rate is reduced by dividing the learning rate by 5, and the training continues as long as the convergence criteria is met again. And again at that, the training rate will be reduced further, and this will continue unless the training rate drops below 10 raised to minus 6. So you can see that here we obtained the mean absolute error on training to be 0.53, and on development set it is 0.51. It took 33 iterations and it performed 383,131 weight updates. So this adaptive learning rate has took longer iterations for SGD to converge because of the style of learning. It reduces the learning rate once it reaches the convergence criteria and continues unless the learning rate drops below 10 raised to minus 6. So we have seen in the slides that empirically SGD converges after seeing about 1 million examples. So here we set max iter to ceiling of 1 million divided by total number of training examples in the training set. and in our case it comes out to be 65. The maximum number of iteration comes to 65. We set this max iter as a parameter in SGDregressor constructor, and we trained the SGDregressor model with the training feature matrix and labels. So even though we have set this max iter to 65, our SGD converges in 8 iterations, and it has performed 92,881 updates in these 8 iterations. We obtained mean absolute error of 0.53 on the training set and 0.51 on the development set. So that brings us to the end of this particular demonstration. In this demonstration, we studied how to build SGDregressor model, how to tune the learning rate, how to use different learning rates and their impact on convergence, how to use early stopping and average SGD. We also learned how to tune hyperparameters with validation curves. We also tried different learning rates and found out their impact on the training. Different learning rates took different number of steps.